Shown here is the B2 MO diagram we just derived with 6 valence electrons. We have the boron 2s. Originally was at minus 15 EVs. So this lowest energy orbital is around minus 19 EVs. And boron 2p is at minus 8.5 EVs. So this highest one is probably around minus 4.5 EVs. And what we're about to do is compare this MO diagram with that for F2. And F has very different energies. Fluorine 2s, here, I'll put it here. Fluorine 2s is minus 40 EVs. And fluorine 2p is minus 18 EVs. So we're about to compare the two. And the first thing we're going to do is just get rid of those tie lines. We'll just look at the actual MOs, which are in black, for the B2 system. And second, because the fluorine orbitals are so low in energy, we're going to make them very small. We're going to shrink down the B2 so we can get to the scale, maybe a little smaller. Good, I'll put them up here. And now we'll put the fluorine orbitals. The fluorine was at minus 40, so way down here we had the fluorine bonding and the fluorine antibonding. Minus 45 EV, oh, not 45, minus 44 EVs. Way down here. Then we have the fluorine P that maybe minus 18 plus 4, minus 22 EVs. Oops. There, I'm sorry that everything is moving. There's the fluorine 2P. Remember that we cannot mix S and P because S and P are 22 EVs apart. And we have very weak pi interactions. So I'll put them here. In fluorine, they're very weak. So I'll put them very close to each other. Bonding and antibonding pi are very close. And then we have high in energy, minus 18 plus, maybe around here, we'll have the, there. Those are the fluorine orbitals. And so this is minus 18 EVs here. And now we're going to do an interesting thought experiment. Let's see if we can make it a little bigger so we can see everything. There it is for fluorine. Imagine that we take boron. So here's boron. We have 2 boron nuclei. And we imagine that we just dump, like, I don't know, like salt. We just dump more plus charges onto the boron. And as we dump more plus charges onto the boron continuously, they turn into other elements. And eventually, boron would turn into fluorine. Now, that's not a real chemical process. You can't just dump a little sprinkle charge. This is a thought experiment. But B2, if you were just to dump in plus charges, would eventually turn into F2. And that means the MOs from B2 in this continual process of adding protons, of charges, should turn into the MOs for F2. The most bonding B2 orbital must turn into the most bonding F2 orbital. The most antibonding B2 orbital must turn into the most antibonding F2 orbital. The pi orbitals from B2, they're going to turn into the pi orbitals from F2. The pi star will turn from B2 to F2. There are just 2 remaining orbitals that we haven't looked at. We haven't determined where they go. This one here and this one here. Here, I'll give them names. A, B, 1, and 2. There it is. Can you see? Look at that picture at 1. It's purely S. And now I'm just going to add a tiny amount of P into it. I add a tiny amount of P. Here's a little P being added. You want to see that again? There's a pure S orbital. That's number 1. And now we're going to see what would it look like if I added just a little P orbital into it. Well, there would be a little nub of P orbital here, a little nub of P orbital here. So, is 1 coming from A or B? Put it in chat. As I just showed, when you add a little P into 1, it comes from A. And when you add, let's look at 2. 2 is this orbital here. And when I mix just a tiny amount of S character, I can make the, here, I'm going to change 2's phasing to the other way around. So it'll make it easier for us to see it. Here's 2. So this orbital is the same as that one. It's just I've changed all the phasing. You can change the phase of all orbitals. And now let's just add a little S orbital into it. We'll add a little of this S orbital into it, and we add a little bit of it. It gets a little bigger on one side, a little smaller on the other. And you can see that 2, when you add a little S, becomes B, so B goes to 2. And so now we see that this is how the orbitals change from going from B2 to C2. Somewhere inside here has to be C2. At some electron count, it's going to be O2. At some electron count, it's going to be N2. At some amount of protons being added, it will be C2. And so as B goes to C, goes to N, goes to O, goes to F, as I continually add electrons, the orbitals must change in this order. And this is a picture from your textbook. As we go from boron to fluorine, there is a crossing. The crossing is right here. I'll put it in green. Right there. For boron, the second highest orbital, from boron, the third highest orbital is a sigma orbital. For carbon, the third highest orbital is a sigma orbital. For nitrogen, it's a sigma. But for oxygen, the third highest set of orbitals are pi, due to this crossing that I showed here. And this is known to be correct from paramagnetism, and there is a shift in the MO diagrams from the earlier homoatomic diatomic to the later ones, and put in chat what's the cause of that. It is the absence of sp hybridization. Why is there no sp hybridization in the case of fluorine? Put it in chat. Why is there no sp hybridization for fluorine? Put it in chat. Because they're too far apart in energy. And why are 2s and 2p so far apart in energy? Starts with the letter P. Why are fluorine 2s and 2p so far apart in energy? Put it in chat. Penetration. The shift in the MO diagrams from lithium, beryllium, and boron, where sigma is the third highest orbital, to oxygen and fluorine and neon, where pi is the third highest set of orbitals, is caused by penetration.